In this lesson, we study the difference between inductive and deductive reasoning. This lesson is very important and it lays a foundation for where we're headed in this class. Inductive and deductive reasoning are essential critical thinking skills used in many different applications. For example, the science of biometrics involves the measurement and analysis of unique physical characteristics. Biometrics are usually used as a means of verifying personal identity. Fingerprints, iris patterns in eyes, facial recognition, DNA, and voice patterns can all be used for personal identification. Some smartphones can be unlocked by pressing a button that recognizes the unique fingerprint, or by scanning an eye to recognize a unique iris pattern. Crime scene investigation often involves fingerprints and DNA evidence. Voice recognition software uses voice patterns of callers to help prevent fraud and to improve customer service. So in this lesson, we're going to understand how important inductive and deductive reasoning are and the difference between the two. Let's start with inductive reasoning. Before we look at some examples of inductive reasoning, let's do a little bit of review. When we talk about the set of natural numbers, we're talking about the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth. Notice that the natural numbers, which, by the way, are also called the counting numbers, so that's like a nickname. The natural numbers are also called the counting numbers. The set starts at 1. So notice that 0 is not included. Notice that fractions like 1/2, 1/3, 7/8, and so forth are not included. Also notice that negative numbers are not included. So the natural numbers, or the counting numbers, start at 1, and then it's every whole number after that. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, and so forth. These 3 dots here, it's called an ellipses. It means that 4 is not the last number in the set, right? So the set continues on indefinitely. It goes on forever, right? And so these 3 dots just mean that the set never terminates. Let's talk about divisibility. If I have 2 numbers, let's say A and B, A is divisible by B means that the remainder is 0. For example, if we say, like, we know 8 is divisible by 4, how do we know that? Because the quotient would be 2 and there's no remainder, or the remainder is 0. That's different than saying 7 divided by 4. 7 is not divisible by 4. Why not? Well, because when you divide 7 by 4, you get 1 with a remainder. I'll just put R for remainder, a remainder of 3. The fact that the remainder is not 0 means that 7 is not divisible by 4. 8 is divisible by 4 because the quotient is 2 with a remainder of 0. And what's important to remember is that the numbers that are divisible by 2 are called even numbers. So the even counting numbers, that means numbers that are natural, that are called even, are those numbers that are divisible by 2. And then the odd numbers are those counting numbers that are not divisible by 2. So like 1, 3, 5, 7, 9, 11, 13, and so forth. These are the odd numbers. So it's just a little recap of what these mean. Okay, let's get into our first official example that shows inductive reasoning, also called induction. Check this out. If 2 odd numbers are multiplied together, will the product always be an odd number? So to answer this question, well, this is what we're going to do. We're going to look at some specific examples. So let's choose some numbers to multiply together and see what happens. All right. All right, so let's play around with this. Let's say 1 times 5. Those are 2 odd counting numbers, right? 2 odd numbers. Whenever we say odd numbers, we mean odd counting numbers. So I don't have to say counting numbers. These are two odd numbers. They're multiplied together. And the product, and by the way, when you're multiplying two numbers, each of these numbers are called factors. So this is a factor, 1's a factor, and 5's a factor. But the answer is a product, and it's 5. That's odd. That's an odd counting number. 1 times 7. I'm just choosing these numbers at random, okay? 1 times 7 is 7. That's odd. 1 times 9, these are two odd numbers, and the product is odd. 1 times 11, these are two odd numbers, and their product is odd. How about 3 times 7? The product is odd. 3 times 9, the product is odd. 3 times 11, I don't know how many of these we want to do. Product is odd. 3 times 13, product is odd. Let's just do a few more. 5 times 9, the product is odd. 5 times 11, the product is odd. 5 times 13, product is odd. 5 times 15, I'm getting more sloppy as we go. The product is odd. And so we can see, obviously there's infinitely many more examples we can pull, right? But looking at this data here, all the products are odd numbers. We chose odd numbers as factors, and the product every single time is odd. Therefore, we might predict, we might conclude from these examples that the product of any two numbers is the product of any two odd numbers is indeed an odd number. So this example is an example of us using inductive reasoning or induction, where you're looking at patterns, you're looking at specific examples to come up with a conclusion. Let's look at another example. Look at this. If an odd number and an even number are added, will the sum be an odd number or an even number? Again, just one more time, I want to remind us that when we say an odd number, we mean an odd natural number or an odd counting number. An even number means even natural number or an even counting number. Okay, so that's just assumed. All right, let's check it out. Let's look at some examples and come up with a prediction. So we need an odd number and an even number, and we need to add them. All right, let's start with, 3 plus 4. An odd number and an even number. The result, the sum is odd. By the way, when you add two numbers or add two terms, these are called addends. Addends. I'll write that out for us. An addend. So you have an addend right here at 3. That's an addend, and 4 is also an addend. And then, of course, the answer is called a sum. A sum. So 7 is called your sum. Anyway, that's one example. Let's look at some more. So odd number plus an even number. And the sum, odd. Odd number plus an even number. The sum, odd. Odd number plus an even number. Sum, odd. Again, I'm just making these numbers up, okay? You can make up your own numbers if you'd like, or use your own numbers. 23 plus 18. The sum, odd. 81 plus 32. That's an odd number and an even number. Oops, sorry. I meant to write equals. The sum, odd. So by looking at these few examples, of course, we haven't exhausted every single example. Of course, that's impossible. Just looking at these few examples, we might make a prediction that indeed the sum of an odd number and an even number is an odd number. Once again, this is an example, as was example 1, of where we make a conclusion or a prediction that the results we're finding are true for all counting numbers. So we're looking at a pattern, right? We're looking at a pattern, and then we're making a prediction like this pattern's going to hold. This pattern will be true for all counting numbers. So this type of reasoning, where you're looking at specific observations, is called inductive reasoning. So here's our formal definition for inductive reasoning. Inductive reasoning is the process of reasoning to a general conclusion through observations of specific cases. So induction is very important in mathematics and in the field of science. Many mathematicians and scientists use induction or inductive reasoning to develop theories and to predict answers to complicated problems. An example might be, or an example that you might want to consider is, imagine you have an endless row of dominoes. You knock down the first domino, it then knocks down the second, and then that knocks down the third, and so on. Assuming this pattern will continue uninterrupted, you may conclude that any one of the dominoes will eventually fall, even though you may not be there to witness the event, because you saw how the first knocked down the second, and the second knocked down the third, and the third knocked down the fourth. So even if you walk away, right, and leave the room, you know eventually the 45th domino is going to fall, as long as everything stays uninterrupted, of course, because you saw the pattern. Okay, so this type of reasoning, inductive reasoning, is an important part, a very important element of something called the scientific method. So when a mathematician or a scientist makes a prediction based on inductive reasoning, based off of looking at specific observations, it's an hypothesis or a conjecture. And so we saw in the previous examples that we made a conjecture or a conclusion, right? Or in this case, a hypothesis, all right? Remember the opening example about biometrics, about how the science of biometrics is used for personal identification? That's inductive reasoning. That's induction. Because after studying millions of people, scientists have never found two people that have the same exact fingerprints, or the same exact patterns in the eye, or the same exact DNA, or the same exact voice pattern. Then, therefore, by induction, a conclusion has been reached, right? That each of these biometrics provide a unique identification. A general conclusion is reached through observation of specific cases. The science of biometrics makes use of inductive reasoning. The science of biometrics makes use of inductive reasoning. That's pretty cool. Check out this next example. Consider the following hypothesis or conjecture. If the last two digits of a number form a number that is divisible by 4, then the number itself is divisible by 4. That's pretty interesting, isn't it? So let's test, I think I forgot some quotation marks here. Let me fix that real quick. There. We will test several numbers to see if the conjecture appears to be true or false. All right, let's do it, folks. Let's make up some numbers. Okay, I just made these numbers up, okay? And so you can use your own numbers. The main thing that you want to make sure when you're making up your own, using your own numbers, is that the last two digits of the number form a number that is divisible by 4. All right, so 324 works because these last two digits, 24 is divisible by 4. We're good. The last two digits here, 28, in the number 4,328, 28 is divisible by 4, so we're good. In the number 10,612, 12 is divisible by 4, so we're good. 21,104, the last two digits is the number 4, and then that's divisible by 4. So each of these numbers that I'm using meet the condition that the last two digits of the number is divisible by 4. Now here's the conjecture that we're trying to prove, that the number itself is divisible by 4, that 324 is divisible by 4. All right, so let's explore. So do the last two digits form a number that is divisible by 4? 24 are the last two digits, and that is definitely divisible by 4 because it is 6. 24 divided by 4 is 6. Therefore, we're saying 324, or the conjecture is saying that 324 is also divisible by 4. And when we check 324, if it is divisible by 4, that means the remainder is 0. And that is actually true. 324 divided by 4 is 81 with remainder 0. Therefore, 324 is indeed divisible by 4. So far, it's working. Let's check the number 4,328. The last two digits are 28. We know that 28 is divisible by 4 because the quotient is 7, the remainder is 0. But what about the number itself, 4,328? According to the conjecture, it is also divisible by 4, which means we will not have a remainder, or the remainder will be 0. And that is true. The quotient is 1,082 with remainder 0. Once again, we found the conjecture to be true. Look at the number 10,612. The last two digits form the number 12. And we know that's divisible by 4 because the quotient is 3 with remainder 0. But the conjecture says 10,612 must also be divisible by 4. And you can confirm that it's true because the quotient is 2,653 with remainder 0. It seems like the conjecture is true. It seems like we're proving that it's true. 21,104. The last two digits are 04, which is just the number 4, right? Is divisible by 4. Of course, it's divisible by itself. Okay. The number itself, according to the conjecture, 21,104, must also be divisible by 4. And you can confirm that it's true. It's 5,276. That's the quotient with remainder 0. So in each one of these cases, and of course, we must keep in mind we've only checked 4 numbers. Does that mean it's true for every single number? Well, inductive reasoning says, after looking at specific cases, right, you can make a hypothesis, you can make a conjecture. And in these cases, it seems to be true. So we're going to say it's true. So we're saying this is true. We're saying this conjecture is true. That if the last two digits of a number are divisible by 4, the number itself is divisible by 4. Yeah, we're going to say it's true. All right, this should be fun. Pick any number, multiply the number by 4, add 2 to the product, divide the sum by 2, and subtract 1 from the quotient. Repeat this procedure for several different numbers, and then make a conjecture about the relationship between the original number chosen and the final outcome. This should be fun to do like on your friends and loved ones, and you can just amaze them using math. Okay. All right. So let's pick a number. Let's say any number. All right. Let's say the number 5. Okay. 5. The first thing we should do after we pick the number is multiply the number by 4. Multiply the number by 4. All right. So this is our original number. Let me label this really quickly before we get too far into this. Let me actually, all right, that's better. All right, the original number is 5. Okay, here we go. Multiply the number by 4. Okay, so 20 is the product. Add 2 to the product. Okay, now I'm at 22. Divide the sum by 2. So 22 is the sum divided by 2. Okay, I get 11. And subtract 1 from the quotient. 11's the quotient, subtract 1 from the quotient, and the answer is 10. Okay, 10 is... What is the relationship between 10 and the original number? 10 is twice the original number. Okay? So I think this example is trying to show that the outcome will always be twice the original number. Let's choose a couple more numbers to make sure like this pattern holds. Okay, let's start with 2. Multiply by 4. You get the product is 8. Add 2 to the product. Okay, the sum is 10. Divide the sum by 2. Okay, the quotient is 5. Subtract 1 from the quotient. I got 4. So the final outcome, the final number is 4, which is twice the original number. It seems like this is working. This is actually really cool. All right, let's choose one more number and then, we'll say, okay, we get it. All right, let's choose another. Let's start with 3. All right, let's go for it. 3 times 4. The product is 12. Add 2 to the product. The sum is 14. Divide the sum by 2. Oops, divide, right? The quotient is 7. Subtract 1 from the quotient. The result is 6, which again is twice the original number. Okay, so we can keep on going, but on the basis of these few examples, and we must highlight that yes, we've only looked at 3 examples, but on the basis of these few examples, we can make a conjecture, right, about this procedure, that the number you end with will always be twice the original number. All right, what's really interesting is the result reached by inductive reasoning is often correct for specific cases, but it's not correct for all cases. So we have to be careful that sometimes we could be wrong. You know what I mean? History has shown that not all conclusions arrived at by inductive reasoning have been correct. So we need to be careful with inductive reasoning. The famous philosopher Aristotle reasoned inductively, so using inductive reasoning, that heavy objects fall at a faster rate than lighter objects. About 2,000 years later, Galileo dropped 2 pieces of metal, one 10 times heavier than the other, from the Leaning Tower of Pisa in Italy. He found that both hit the ground at exactly the same moment. So they must have traveled at the same rate. You know what's interesting? The astronaut David Scott from Apollo 15, he used the moon as his lab to show that a heavy object, he used a hammer, does indeed fall at the same rate as a feather. Had Galileo dropped a hammer and feather from the Tower of Pisa, the hammer would have fallen more quickly to the ground, and he would have concluded that the heavy object falls faster than the lighter one. So what's the deal? If it's not the object's mass that is affecting the outcome, then what is it? The answer is air resistance, or friction. Earth has an atmosphere that creates friction on falling objects. The moon doesn't have atmosphere, therefore there's no friction. So again, these are just examples of mathematicians and scientists and philosophers and astronauts that are looking at specific cases, right? Making observations from specific cases to make a prediction, to make a hypothesis or a conjecture. Now, when we are forming general conclusions using inductive reasoning, we should test the conjecture, the hypothesis, with several special cases to see if it's correct. If you find a case that satisfies the conditions of the conjecture, like for example, earlier we're looking at numbers where the last 2 digits form a number that is divisible by 4, those were the conditions of the conjecture, right? The number that you choose to use to test the statement, to test the conjecture, they first must meet the conditions, right? So if you come across a special case that satisfies the conditions of the conjecture but produces a different result, has an outcome that contradicts the conjecture, that's called a counterexample. A counterexample proves that the conjecture is false. Okay? Because you only need one exception to show that a conjecture is not true. A conjecture is not valid. All you need is one example that shows it's not true. You just need one counterexample. Like, for example, Galileo's example where he dropped two pieces of metal from the Tower of Pisa, one 10 times heavier than the other, and they fell at the same rate. That counterexample disproved Aristotle's conjecture. You know what I mean? So Galileo found a counterexample. Now, for you and I, if we cannot find a counterexample, then the conjecture is neither proven nor disproven. It's kind of inconclusive. Okay? Consider the following. If someone made the statement, all birds can fly, right? And this person studies different birds, right? Looks around, sees a blue jay, it's a bird, it can fly. It sees an eagle, that's a bird, it can fly. Sees a hawk, that's a bird, it can fly. Sees an owl, that's a bird, it can fly, right? And sees a bunch of different birds and they all fly. That person may be tempted to make the conjecture that all birds can fly, right? But all you need to do is see a penguin, for example. A penguin, a bird, it does not fly. Therefore, a penguin is a counterexample to the statement that all birds can fly. All you need is one example, right, that proves, that has a different outcome, that proves the conjecture is not valid. All right, cool. We're now going to move to another kind of reasoning called deductive reasoning or deduction. Okay? Here's the formal definition for deductive reasoning. It is the process of reasoning to a specific conclusion from a general statement. For example, okay, let's use deductive reasoning this time to prove that the procedure given in example 4, do you remember the previous example where we pick any number, we multiply that original number by 4, add 2, divide by 2, subtract 1, and then we said, after looking at specific examples, we said, oh, the final number, the outcome will always be twice the original number. We used inductive reasoning before. Now, let's prove that conjecture is true using deductive reasoning. All right, if we're going to use deductive reasoning, we need to start with the general case. We don't look at specific cases. We look at the general case. So when they say pick any number, let's say the original number is n. Okay, so that represents the original number. The procedure in the previous example, in example 4, says the first thing you do to your number that you pick is multiply by 4. All right, so let's go. Your original number times 4. The product will be 4n. The next thing it says is, in the procedure, is add 2 to this product. Okay, so here's the product, 4n, and we're supposed to add 2. Okay, that's just 4n plus 2. You can't, like, simplify that or anything, so it's just 4n plus 2. The next step in the procedure is to divide this sum by 2. So now I'm taking this sum, 4n plus 2, and I need to divide it by 2. If you're going to divide this sum, 4n plus 2, by 2, you have to divide each term by 2. In other words, you have to divide 4n by 2, and you have to divide 2 by 2, right? And that gives you 2n plus 1. The next step in the procedure, I'm going to move the screen a little bit. The next step in the procedure is to subtract 1 from this quotient. So 2n plus 1 is the quotient, and I'm supposed to subtract 1. And the result is 2n. What is that? 2n is twice the original number. So no matter what number you select, for this procedure, the result will always be 2n, or twice the original number selected. So because we started with n, the general case, that's what we started, that's what we began with, this is called deductive reasoning. Now, what's really important is that in the previous example, in example 4, where we looked at specific examples, we use inductive reasoning, right? And we made a conjecture. This is very important, we made a prediction, but we did not actually prove this statement that you always get twice the original number. We didn't prove it. We made a prediction or a conjecture that that statement is true, but we didn't actually prove it. It's using this kind of reasoning. Deductive reasoning is the type of reasoning that is actually proving the statement, proving that you get twice the original number. So that's very important. Inductive reasoning is going to allow you to look at specific examples, and then you can make a prediction or a conjecture. You're not proving it, though. It's just a prediction or a conjecture. You could be wrong, right? But in deductive reasoning, we can actually prove the statement is true.